Yeah, go for it.
All right. Thank you. So, hey guys, I hope everyone's doing all right. I hope you had at least a starting with a good weekend. So, I wanted to talk about about two pretty good papers that kind of piqued my interest during my time as a deep chem developer and also as an undergrad because I come from a physics background and understanding and implementing both of these concepts, merging physics and machine learning, were pretty interesting. So, which is why I thought it might be a good idea to talk about both of these papers at the same time. Because at the end of the day, both of them are actually pretty similar, and I'll touch on that in the presentation. So, decoding physics with neural networks. So, to give you a short synopsis, what happens is integrating physics systems with traditional neural networks has always been somewhat of an issue because you are constrained by specific laws that most of us are well aware of. Conservation of energy, momentum, angular momentum. It could be an n number of laws that constrain systems, and due to these postulates and constraints that seem very natural to us, are sometimes confusing for neural networks to understand. And so, for that, we work on a system that tries to implement these constraints into the neural networks themselves. So, I guess we can go on to slide 3. All right. So, right. Here, let's start with the introduction. So, accurate models of the world are built upon notions of its underlying symmetries. In physics, these symmetries correspond to conservation laws, as we talked about. And the biggest issue is that to realize these systems, we need to respect these symmetries, and for that, we need to actually implement these physics laws into our neural networks. And that has been successfully done in 2019 and then 2018 with the two papers that I'm going to talk about. So, next slide. All right, so this is a quick refresher on classical mechanics and to really get an idea of what we're going to talk about. It's going to be you're going to be very familiar with these concepts. So, like going through all of this is going to be a breeze. So, all of us are well aware of Newton's three laws of motion, and we are also quite aware, like we have practiced in high school as well as in undergrad courses, on how to basically break down complex systems and formulate these equations of motion. Now, this classical mechanics is, or rather, more accurately in this scenario, Newtonian mechanics has always been difficult to integrate with machine learning models because it is very difficult to create an arbitrary formula or rather a generalized formula that can work for any system. So to solve this problem of generalizability, uh, we came up with Lagrangian and Hamiltonian mechanics. So like just a quick disclaimer, everything over here might be oversimplified and that's kind of my intent. I just want to make sure that whatever concepts you're going through are just very easy to understand. And so we keeping that in mind, we get into Lagrangian and Hamiltonian mechanics. So in Newtonian mechanics, what we find is if, for example, if we take an example of a pendulum, what we would do to find out its equations of motion is to go through an extremely long process to figure out the relation between the momentum and the velocity and the force or of the pendulum swing at any given point. And to realize this, as we have mentioned before, is quite tedious process. So both of these processes, Lagrangian and Hamiltonian mechanics, are basically like a hack, if I can say so myself. Because all we need to really understand from a system is its energy. If we know the energy, if we know the kinetic energy and the potential energy of a system, we can basically understand everything about a system. And that's the best part. Now, how that happens is because of, like we mentioned here, a clever reformation of Newtonian mechanics and the stationary action principle. So, I'll just go over what stationary action principle is. Like it's still on slide 5 right now.
Oh, sorry.
So if we go through the entire text, a true dynamical trajectory of a system between an initial and final configuration in a specified time is found by measuring all possible trajectories of the system that it could conceivably take. And the true trajectory of that system is always going to be the one that has the least action. Now, this might sound like a bunch of jargon right now, but now when we go to the next slide, slide number 6, it's going to be a lot more clearer because now we can actually realize it in mathematical formulas. So, the idea of action is basically to find rather the energy difference between the potential and the kinetic energy at any given point in the path. So, as we mentioned before, they can to go from point A to point B, or rather to state A to state B, we can take infinite paths. But in reality, we'll realize that there's going to be only one path that is actually manifested, and that is where the least action principle comes into place. So, to put it very simply, if we can go through the final formula, the least action taken is the one that is actually realized in mechanics. So that's the entire principle that Lagrangian and Hamiltonian models work on. It's basically if you find the difference of the energy, or rather the energy uh, constants of any single system, we can kind of find out every single thing there is to know about a system. So to understand that more, let's take on a more specific example when we go to slide number 7. So now that we have talked about the least energy principle, we can kind of understand a bit how these systems could take in energy, right? So to understand that properly through Lagrangian mechanics is quite simple, and that's the idea of the little differential equation that we have here. So if we go through a step-by-step process, Lagrangian as a function is basically the difference between your kinetic energy and the potential energy of the system. So if you find the difference, that is the Lagrangian. And to find every single information that there is to know through Lagrangian mechanics, all we really need to do is follow this differential equation. And once we equate it for a generalized coordinate, we are going to basically get the equation of motion for that generalized coordinate. And that's the best part. Like if we compare this directly to Newtonian mechanics, we'll realize that instead of going through all of this jargon, we can just follow two rules. We have the energies, we find the Lagrangian, and then we simply follow this equation, and then we get our equations of motion. So in a very similar fashion, we also have the Hamiltonian function. So that would be in slide 8. So the beautiful part about Hamiltonian mechanics is that it basically is a restructuring of the Lagrangian mechanics, but instead of finding the difference of any system, we are instead finding the total sum. And that creates a beautiful symmetry because then we realize the principle of energy conservation also. So because of the energy conservation laws, the it's very easy for someone to find, let's say, the specific coordinates or the specific momentum of a system using whatever parameters that we have. So calculating Hamiltonian is a very simple process. We just need to find out the sum of your kinetic and potential energy. That's one way. The other way is to follow the equation that we are given in the the first image, the first differential equation. So it effectively just translates into the same thing, that the Hamiltonian of a system is just the sum between your total energy and your potential energy. But this helps us create an effective transformation between Hamiltonian and the Lagrangian. So one thing that we can also see is the parameters that are involved in both the Lagrangian and the Hamiltonian. Because at the end of the day, while we are working with deep learning models, we are most interested in determining what parameters can work. And here we can see that the Lagrangian and the Hamiltonian have different parameters. That is, the Hamiltonian has momentum as well as the coordinates, whereas the Lagrangian has the coordinates and the velocity of any single generalized coordinate. So now that we can basically visualize both of these ideas in the form of formulas, it becomes very, very, very intuitive for us to build them into neural networks. And that's what we'll get in the next slide. So finally, we are about to understand how the models actually work. So the idea is that I'm going to show both how this model works, the training scheme, and then after that, we're just going to go through the papers and then understand it a little bit better. All right. So before we go to that point, are there any questions or any doubts that we might have at this point?
Sorry, one question from my end. Sorry, it's a very basic, but for Hamiltonian, basically you get the differential equations of the moment, the generalized moment and generalized coordinate. And for Lagrangian, you get just for like the velocity and the position, like differential equation, basically.
That's correct.
Okay.
And the reason why it's in that particular way is also very interesting to understand is because Lagrangian in itself contains both of those realizations. So again, this might be a bit complicated, so I did not add it in the slides. But basically, both the left side and the right side are essentially a realization of Newton's third law, where F is equal to ma.
Uh,
So I felt that the derivation might be a little bit irrelevant, so I didn't feel to add that in. But it's also pretty interesting.
okay. And sorry, another basic question. For the Hamiltonian is the total energy in the system, right? So it's always constant. So,
Absolutely. Absolutely. And that's another interesting thing that if you actually try to find the change of the Hamiltonian value over time, it's always going to be zero. And that's actually how we get the equations below. We equate it, we find del H by del T to be zero, and then we break it down with the individual variables, which is the generalized momentum and the generalized coordinates. And that's exactly how we get the equation below. It's because of the total energy, the change of total energy being zero over time that we get these equations.
got it. Thank you.
All right, perfect. So I guess it's time to like go over how H&Ns work. So I feel one way that we can understand it is through the diagram itself, because this was provided to us by Sam Gradanis, the author of the H&N paper. So, traditionally, to find the momentum and the velocity of any system, which is q dot and p dot in this example, we would generally have a ton of issues that's basically coming because of the uh, more or less what can we a better way to rephrase it would be, since neural networks cannot establish basic conservation laws like we mentioned before, it's not able to realize these systems and it's not able to generalize them no matter how powerful the neural network is. So if we see this example, this is a simple mass spring system, and if we see the prediction from the baseline neural network, we would realize that it's not in a single circle, which ideally it's supposed to be. And that's because it's not able to understand that the Hamiltonian, or rather the energy of the system, has to be constant. If it did, it wouldn't have this variation. So the entire idea of Hamiltonian neural networks came from this single model, where instead of directly finding the generalized velocity, the generalized momentum of the system, we create an intermediary neural network that first tries to find out the Hamiltonian of the system. So if we go through this, we basically have simple noisy data as input, and after that we take the input coordinates, like in this case being the generalized coordinates and the momentum, and then we try to find the Hamiltonian of the system. And then using those Hamiltonian values, we are able to find both P dot and Q dot. And if we go to the next slide, I think we'll be able to understand it a little better. So basically, the entirety of Hamiltonian neural networks is just in this one slide, because it contains more or less every single thing that you need to know about how it trains, how it optimizes, and how it finds out the values that we talked about before. So Q dot and P dot, which are basically the time derivatives of the generalized momentum and the generalized coordinates, can be found out through this simple equation that we have already established in slide 8. So it's the exact same formula, and it's just a clever way of introducing it here. Now, the thing that they try to integrate was to find out the future states as well. So if you're starting with an initial state, you would also want to find out where the specific object, or rather the specific body, is during a certain time period. And that's exactly what they try to accomplish here using the time derivative. And it's very intuitive to understand. I guess it's a bit confusing to start with, but it's, again, if we go over the formula a little bit, it might be easier to understand. So the variable s over here is basically just the generalized velocity, or rather the change in generalized coordinates and the change in generalized momentum, the same values that we found out above. Now, if you're trying to integrate a derivative of a function, it's, if we remember calculus, we would realize that it's just the change in those values from t1 to t naught. And that's the beauty of this equation, because instead of creating a whole another equation or whole another process to find out these new states, we instead just use the states that we already have, and then we take that we integrate it over a certain time period, and then we get the change required to add it on and get the next state. And that's how we basically get a newer state from an older one. And that's also how you get a chain of states, and you're able to visualize the system in its entirety. And also, another thing that I cannot absolutely forget to mention, if we are trying to optimize a model, we of course need a loss function. And Sam Gridanas came up with a very, very simple formula that is very intuitive for us to understand. It's basically the Euclidean distance between the predicted values, or rather the predicted change of the time derivatives versus the actual uh, time derivatives that we have in our training data. So if we simplify this formula of LHNN, we'll find out that it's essentially just dq by dt of the predicted values subtracted by the change of coordinates from the original training data. And then you have the same thing going on for the generalized momentum. And that's essentially how you get it. And all of this is L2 distance, or other Euclidean distance. So again, it's a very intuitive formula. It's very easy for us to understand. Might be a bit confusing because we haven't gone through the paper yet, but it's easy for us to visualize a bit how the model is going to train and how it's going to run. So if we go to slide 11, we see that the training and the testing phases of the model have been put in separately, because there is some slight difference. So if you're going to train the model, it's basically simple 5 steps. We start by initializing the neural network, and we have Q naught and P naught as our input vectors. And since we know that our neural network is basically trying to find the Hamiltonian of our system, we get the output, which is mathematically equivalent to our Hamiltonian, right? Now, since our goal is to actually find an accurate representation of the Hamiltonian, what we're going to do is try to find the time derivatives of the coordinates. And then using these time derivatives, we compare how accurate these results are in comparison to the time derivatives that we have in our training data. And we optimize the network using the loss function that we just talked about in slide 10. And that should be enough to train the model. And to test the model, which again, like we discussed, our goal is to find out not only the values in our current state, but also to find out the future states. So we initialize the neural network with Q naught and P naught, and then we find the Hamiltonian, we find the time derivatives. But now we try to find the states Q1 and P1 using the time evolution relation that we figured out previously. And once we have Q1 and P1, we are going to input that to our neural network, and then we're going to get new states, and then this process will continue till a certain degree, or like as soon as we stop the execution. So this is how you train and test the models. And if like before we go on to Lagrangian models, we'll just, if there are some more doubts, we can go over that. Or if you want, we can just go through the paper and kind of see what it has for us.
Uh, I have actually, let me invite the speaker.
Hi. So I'm a little confused by what we did. So in both the Hamiltonian and Lagrangian picture, of course, the equations of motion that you get in the end are the exact same as Newton's equations of motion, except for the fact that you have a first-order differential equation in the case of the Hamiltonian formulation rather than a second-order differential equation. And it seemed in the end, the only thing that we used was Hamilton's equations for this neural network, right? Like your loss function was just in terms of making the Euclidean distance for making the differential equation 0, right?
That's correct, right? Okay,
So I
so I
guess
guess I get what
like
it.
what did we? Oh, sorry.
No. You first. My bad.
What did we gain by doing this? Why was it good to go to the Hamiltonian picture?
All right. So the biggest advantage that I felt while reading through the paper was the fact that we were able to simplify or rather generalize all possible formulas or other possible states of equations using a single standard formula. That's kind of why we prefer Hamilton and Lagrangian mechanics over Newtonian, even though at the end of the day, all three of them will give the same output, because these, like, I think there is some confusion over here. Lagrangian, Hamiltonian, as well as Newtonian mechanics, all three of these mechanics are pointing towards the same solutions, because at the end
Yeah.
of the day you will have the same states of motion, you will have the same velocity and the acceleration. The only difference is how you reach them, or rather how easy it is to find those calculations. The issue with Newtonian perspective is that once you have enough generalized coordinates, it becomes very difficult and very tedious for us to calculate, or even better yet, to generalize those states of motion. And that's kind of what we get from Hamiltonian and the Lagrangian perspectives, because you're able, not only are you able to generalize them, but you're also able to create a simplistic method for you to follow, and that helps us in computing all of these values.
Sorry. So when you say you're not able to generalize the equation, sorry about the noise. When you said you're not able to generalize the equations of motion, like what do you mean? You mean like you're more generically are going to have a system where you're like in some constrained set of coordinates, and that's the benefit of looking at Hamiltonian Lagrangian mechanics. So uh, I know that, for example, when you have a constraint, it's more difficult to look at Newtonian equations of motion, because the constraint requires you to like basically find an equation of motion that makes sure that you always stay, an additional equation of motion that makes sure you always stay on a constraint. Um, and so,
Right,
sorry, was
that's
that what
exactly
you're
what.
referring to?
I guess that's a better way of putting that because, again, with Newtonian mechanics, at least from my experience, I haven't been able to generalize one set of problems to another set. So let's say if you're working with, let's say a triple pendulum problem, and then you have something like a two-body problem. What we would realize
Okay.
that the way to find out the equations of motion for both of them happen to be very different in the sense that the operations that you have to perform to get to those equations of motion are very different for both the two body problem and the triple pendulum problem. So it's just that when you have different constraints, when you have different systems going on, and you have multiple new implementations, right? It becomes very difficult to kind of create like a universal solution to say, "Ki, right, if I use this formula, or rather, if I use this technique, I would reach this answer. I would reach these equations of motion." So that's kind of the issue with Newtonian mechanics. Again, all three of
Okay.
them, uh, right? I
Yeah,
think
yeah,
was
I think that makes sense. That if you're looking at a constrained problem like a pendulum, there is something inherently more difficult about looking at the Newtonian picture. If you've chosen if you didn't choose the angles as your coordinates, it would be very hard to derive. Or that's easier if you're in the Hamiltonian or Lagrangian picture. The one other thing was earlier you said that the Hamiltonian is always preserved, but you had it evolving with time. If the Hamiltonian or Lagrangian is time dependent, energy is not conserved, right? But anyway, that's just like a small note.
I guess I didn't explain that properly. I'm really sorry. What I Okay, are you talking about the slide where like we introduced Hamiltonian and the Lagrangian as functions of time, or was it during the
Yeah,
Hamiltonian neural networks?
yeah, it's not so important. Like here, yeah, exactly right. One slide back. Uh, no, forward, I guess.
I guess slide eight.
Again.
I believe that's slide eight.
Yeah, exactly. This one. So like if h of t if h depends on t, h is no longer conserved in time anymore. The h will have an equation of motion that just looks like the total derivative
Right,
of
right.
h is equal to partial t of h. But anyway, it doesn't. That is not important. Anyway,
No,
okay,
no, I completely understand.
keep going.
I think I understand that issue as well. So that's on me. But what did mean to say was that Hamiltonian is going to be conserved of time, and the way rather the first equation is rather meant to form a relationship between Hamiltonian and Lagrangian. I I guess that's the time dependency really kind of messed it up.
That's all good. All right. Excited to hear the rest of it.
Thank you. And I guess we have another question. So Lagrangian and Hamiltonian neural networks are more parallel in nature. Absolutely, absolutely. It's rather the Hamiltonian Lagrangian mechanics, as we have mentioned before, because all everything related to classical mechanics, whether it be a Newtonian perspective or a Lagrangian or a Hamiltonian, all three of them give the same solutions. It's a better analog would be if you had three ways to solve a problem. Would you prefer something which is more methodical, or would you prefer something that is more tedious, or rather very specific to a specific problem? That's kind of the issue that we're trying to solve here. Template is a better word. Yes. So it's very easy for us to realize these systems using both of Hamiltonian and Lagrangian. So that's kind of why it's kind of cool to look at it. Yes. So, right. I guess that makes a little bit more sense now. If it doesn't, then that's not an issue because we'll be like we're just going to have a small like quick glance at the Hamiltonian paper because I do believe I'm not giving it enough the justice it deserves because it is really cool. So, Chad, if it's all right with you, like, can we go to the paper? I guess it's
Sounds good. Sorry, one question from my end. So for HNNs, the output of the model will be for the Hamiltonian will be like Hamiltonian in terms of P and Q. Like it won't be like a numerical value, it'll be like coefficients.
Absolutely.
Okay, gotcha.
Right. Okay then. So if once we go through the entire paper, I believe it's going to be much more easier because quite frankly, they have put it in definitely a better way than I could ever explain it. So, but yeah, I think it's worth going through. So, let me share the link again if that's so right. So I guess this is the same link.
Should I click on it?
Huh, yes,
Okay,
yes.
so sorry. Sounds good.
All right, so it's going to be like a very, very quick overview of what the paper has to offer. So again, if we go through the diagram once again, it might help us understand it a bit more uh, in a better way now that we know how it works. So again, in baseline neural networks, the goal is to find out the entirety of the system using first finding the velocity and the momentum of a system, and then using both of those to find out the next states, and then continue that entire process till we have a complete idea of what the system is. Now, the issue with that, like we mentioned, is conservation. And so to solve that, we created Hamiltonian neural networks, which focus specifically on energy conservation. And how it does is we can, if we go to section 2, which is on page number 2, here it is. So again, we can see the time evolution formula, and it's nothing, this formula isn't specific to just Hamiltonian neural networks. This is rather just a clever way of saying, right, if I am at this state q0 and I want to go to a state q0 plus delta q, how would I find delta q? I could find delta q by either using the velocity at that specific point and then finding the change of my position from point zero, point time zero to point t1, and that's exactly what this is trying to say. So it's nothing specific, it's just a very clever way of mentioning something. And if we just go with the para above it, I guess that explains it in a better way. So the first problem is its notion of discrete time steps that connects neighboring states. So that is kind of an issue that has been covered above. I'll get into that a little bit later if we can. Since time is actually continuous, a better approach would be to express dynamics as a set of differential equations and then integrate them from an initial state t0 to a final state t1. And again, like we said, that shows how easy this is to visualize. All we are really doing is, instead of finding the change in steps, we're just going to find them in a continuous manner, and that helps us in our computation. And so equation 1 shows how it might be done, letting us denote time derivatives of the coordinates of the system. This approach has been underexposed so far, but neural ODEs take a step in the right direction. So right, ordinary differential equations are also using time evolution formulas to find next states. So, but I guess that's not in the scope. The second problem with existing methods is that they tend not to learn exact conservation laws or invariant qualities, which we have touched on. This often causes them to drift away from the true dynamics of the system as small errors accumulate. And if, like, once we have already seen how that works in simulation, we saw how the relationship between P and Q was getting skewed over a specific because of the lack of energy conservation. So to solve that, we have Hamiltonian mechanics, and again, Hamiltonian mechanics, William Hamilton introduced mechanics in the 19th century as a mathematical reformulation of classical mechanics. Again, it's, as we have touched on so far, its original purpose was to express classical mechanics in a more unified and general manner. I guess this is a better way to explain why we would prefer this over anything else. Because it's generalized, it's easier for us to use it as a template for anything else. So over time, those scientists have applied it to nearly every area of physics, from thermodynamics to quantum field theory. Hamiltonian mechanics, we begin with a set of coordinates q and p. So now one issue that we do have here is that while Hamiltonian mechanics does use generalized coordinates and does use generalized momentum, there is a specific constraint that we have that actually makes it a little less usable for most tasks that we'll touch on a little bit later. So taken together, they offer a complete description of the system. Next, we define a scalar function h, which is the Hamiltonian, so that we could find the relationship between position and the momentum using the Hamiltonian. So we have already explained that, so it's nothing completely out of the ordinary. And we can also see how the moving coordinates in the direction sh gives us the time evolution of the system. Now, with this, we can understand how S is working. In the next line, we can see we can think of S as a vector field over the inputs of H. In fact, it is a special kind of vector field called a symplectic gradient. Now, this is something that might be a little bit complicated to grasp in the first try. But if we move on further and we try to understand what the authors are trying to prove, whereas moving in the direction of the gradient of h changes the output as quickly as possible, moving in the direction of the symplectic gradient keeps the output exactly constant. And this is why we prefer this over anything else. So moving in the direction of the gradient of h does change the value of the Hamiltonian to find the minimum value of h. And since we are changing the value of the Hamiltonian function, it ruins the entire point of energy conservation, and therefore the answers are not going to be as accurate as they have to be. So by moving along the symplectic gradient, we are basically ensuring that whatever step that we take, our gradients are going to be exactly constant. The Hamiltonian is going to remain constant for the entirety of the execution. So Hamilton used this mathematical framework to relate the position on the momentum vectors of a system to its total energy. So E total is equal to h QB. We have already established that. We already know that from the derivation we have done before. And then he found SH by using equation 2 and obtained the dynamics of the system by integrating this field according to equation 1, like we have already mentioned. So this is a powerful approach. Right, over here, right, correct. So this is a powerful approach because it works for almost any system where the total energy is conserved. All right. So now we're just going to make sure that we wrap this over so that we can go to the next part. And we can find the loss function by finding the L2 distance between our change in generalized coordinates and change in generalized momentum. And again, this is very intuitive, and there's obviously a scope for experimentation, but I think that kind of strays away from the point of the paper. So now everything from section 3 onwards is going to explore how Hamiltonian neural networks work. And I think this is a good idea. It gives us a good idea of how these models can actually help us out. So again, they have gone over multiple tasks, and each one is more impressive than the one before it. So it's worth checking it out. It's going to be a quick jump though. So for an ideal mass spring, we have your spring constant, and then we try to find the entire Hamiltonian function as a function of your coordinates as well as your momentum. So Q and P. So again, the Hamiltonian can be represented in this form where it's related to the spring constant K, the coordinates Q, and then the momentum P. And once we go over the other task as well, I guess we can see the results together. For an ideal pendulum, again, we'll just skip over this as quickly as possible. So P is again the momentum, L is the length of the pendulum, and M is the mass of the ball. So that's that. And then a real pendulum. This is something interesting because they actually implemented a environment and used image data to find this out, which is very interesting. So which is also the reason why I wanted to focus on this paper. because that is something that the Lagrangian neural networks hasn't worked on. So this also works on image data, just to be clear. So yes, right, all right. So let's just go over the results. All right, so if we go to, we'll start from the bottom up. We'll start with the real pendulum and then followed by ideal and then the ideal mass spring. So, and that kind of shows how powerful these neural networks are. So if we can see over here in the real pendulum, we have the ground truth in black, we have the Hamiltonian neural network result in blue, and the baseline neural network model in red. And we can see that the since again, and it did not consider energy conservation, and so therefore it immediately started to converge, and which isn't really that surprising, but I thought it might be interesting to add. And if we can go through the loss and we can see the performance, we can easily see why baseline neural networks are not good for physical realizations, and that kind of gives more credit to these networks that actually integrate classical mechanics. So if you go, all right, right, so we are using the MSE error, so that's right. So again, now we'll go to the real pendulum. We have already gone through that. So ideal pendulum, right. So, in the ideal pendulum, it's pretty interesting because we can kind of guess that the baseline neural network was performing somewhat closely, but we can also see that it deviates at many points. If like if you can zoom in a little bit, yes, perfect. Exactly. So it is kind of deviating and actually going out of course. And the same thing is happening for the ideal mass spring system as well. Yes. So instead of like exploding outwards, it's converging inwards. So it is pretty interesting to see how effective classical mechanical systems are and how good they can work as neural networks. But the more interesting result that I wish to show here was there are actually two. So there is two body problem as well as a real pendulum system that I'll show. Um, uh, Chad, would you like to go to, I guess, page number 6? Right. So I this actually gives us a better idea of how effective neural Hamiltonian neural networks are over traditional neural networks. So the two body problem is basically uh, involving two objects with a specific mass. In this case, having equal mass, and then having them tug each other around using a, like in this example, let's take gravitational force. So the two body problem is basically just two bodies just going around each other, either using a static field or maybe using a gravitational field. So just for the interest of making this as quick as possible, I'm just going to skim over the results. But we can easily see how the baseline neural networks just immediately start converging onto one another. And that's pretty interesting to me. Also, one another issue that we can see with the Hamiltonian neural networks as well is that they are also kind of going outwards. Now, this also brings on another issue from the model, and I guess they have also explained that in the results. Right. So, right. Okay. So, if we go to results 4.3, the HRN model scaled well to the system, and okay, second row a slower rate even as okay, all right, so this is all for figure 3. So we can see after one orbit the baseline dynamics have completely diverged from the ground truth, whereas the HRN dynamics have only accumulated a small amount of error. As we continue to integrate up to T50, uh can we go to 4.2 if we can? Yes, so 4.2, yes. Right, so this will just give us an idea of how well these models are working as well. So if you go to the second paragraph, After one orbit, the baseline dynamics have completely diverged, and the HNN dynamics are actually only accumulating a small amount of error. Although in our case, it is pretty noticeable, but the fact that it actually didn't deviate that much does give some credit to the model. And as we continue to integrate up to t equal to 50 and beyond, both models diverge, but the HNN does so at a much lower rate. So that's that. Again, this kind of shows how some problems are still worth like working on. Right. Averages from the ground truth orbit and the total energy remains stable rather than decaying to zero or spiraling to infinity. Yes. So again, it's still following energy conservation, but it is still failing a little bit. And that is definitely something that the authors have not accounted for even in their future papers, at least according to me. So from what I've seen, they haven't actually taken this specific error into account. But another thing that I did find interesting, and I am kind of disappointed that nobody has tried again after this, is the fact that if you go to section 5, uh, yes, over here, they were able to successfully use the Hamiltonian models with image data. So not only was it able to predict on numerical data, it can also use an autoencoder to encode image data into the specific momentum and position coordinates, and then can calculate the predicted values using that. And I like the first time I read that, I was completely shocked. So I believe it's a little bit, it's worth your while to have a look at it. So I'll just skip over how they actually did it. They use an OpenAI gym environment to run it all. So they created this gym environment and they used image data to actually create this data set. And then they use an autoencoder to go over and basically create a relation between the input image and related it to the two variables that we have. And those two variables, which is the momentum and the position, and they can be inputted into a Hamiltonian neural network, and we already know where it goes from there. So if we go to page number 7, okay, so here we are, and this is absolutely mind-boggling. Even though I've seen it a couple times already, it still just breaks my mind because the ground truth and the result from the Hamiltonian networks is almost identical. And if we see the pendulum angle, we can also see that it's in the exact same phase, although with lesser amplitude. So that really puts into perspective how good these models are in comparison to traditional networks. So that is something that I found really interesting. All right, so I guess everything other than that might be a little bit more complicated and might take more of your time. So, Chad, if you're willing to, let's go to the Lagrangian neural networks. Thank you, thank you. So, I guess since we have already established how similar Hamiltonian Lagrangian methods really are, it shouldn't be surprising to see that both of these methods are essentially extremely similar in the way that they work. So again, like in Hamiltonian neural networks, we had an input variable which was q and p, and then we had to find out another set of variables to find out the next states. So that's the same thing that we're doing over here. Although instead of using the Hamiltonian as a function, we are going to focus on using the Lagrangian instead. So if we just go over this, LNNs were created in a very similar fashion, as we mentioned. And this is something that has been acknowledged by the authors themselves, as you can see here. So, like, one thing that I did forget to mention is that Sam Gradanos is actually who is actually the author of HNNs, is also a co-author in the Lagrangian paper. So it's no surprise that they are actually very similar. But there are a couple changes that work in favor of Lagrangian networks, and which is something that I will touch on with the paper. And if we, like, as one might expect, the training and evaluation of the model is also similar, but there are some differences again with the parameters and the objective. Here, the parameters are going to be the generalized velocity and the generalized position. And then for the output variable, we are going to have the generalized acceleration of the system, which, if you realize, is quite different from what we had before. So another notable change is that we don't need to explicitly find the time evolution of states. This is something that you'll see in the paper as well. They did not go into the time evolution formula or how they used it. What they did mention was the use of the generalized acceleration. All right. And there's another big change that they did include, or rather was kind of implicit, that we'll touch on later. But again, just to make sure that everything goes as smoothly as possible, we'll just go to the next slide. Yes. So, unlike Hamiltonian neural networks, the prerequisites to understand LNNs is even lesser. Although this formula in itself is a pretty tedious derivation, so we'll leave that for the paper. But the idea is to find the generalized acceleration and to also find this acceleration using the current hardware that we have. The authors came up with a vectorized solution. So this might seem a little bit scary because it definitely did to me, but the idea is pretty straightforward. They use the vectorized notation of the Lagrangian mechanics and just transformed it to find the value of the generalized acceleration. So this is for what we have for Lagrangian neural networks, and then we'll go straight to the paper. I'll send the link, Chad, if that's fine with you. Chat going on the rabbit hole and did point out that. Ah, wait. Could you give me some more info about that, Shriki? Also, if I guess if it's comfortable with you, you can also like speak up in the group, and I think that might be a little bit easier for you as well. I was talking about in types of neural networks. Okay. All right, bet. All right, bet. So, if there are any other questions that might lead up to the Lagrangian paper or something that we have already covered, and you have a doubt regarding that, like I'd be more than happy to work on that.
Yeah. So I guess I'm slightly confused by why they claim this works in the paper, because of course, you know, the equations of motion for the system sort of regardless conserve energy at the, you know, infinitesimal time step level. And the divergence that you get from that is from integration error. It's from having a time step which is too long. The systems that they're showing for the ideal systems are, of course, like energy conserving only. And I guess the point is that this form of neural network forces energy conservation, where the other form of neural network has a very arbitrary force law. But then the system that they're showing, a real pendulum, of course, doesn't have energy conservation because it has friction. And you can see that the real pendulum is decaying away from the Hamiltonian neural network's prediction, but that the baseline just does much worse for some reason. I would say it's still confusing why what they're doing sort of is, for the ideal systems, it's clear why it would be more effective, just because they're enforcing energy conservation where the baseline has no enforcement. But it's not clear why it should perform any better on the real pendulum. I guess the real pendulum, maybe they only show like a very short evolution here. Maybe it's just that the real pendulum, uh, they didn't let it evolve for long enough that you like saw the loss of energy conservation or something like that. But
Hmm.
the reasoning about the symplectic uh, gradient would equally be true if you had Newton's equations.
Okay.
Do you see what I'm saying?
I think I get what you're saying, and that is an interesting observation because that's kind of what I felt when I read the paper first. So, this is why I
It's
feel right. You first.
no. You go ahead. Sorry.
All right. So again, the reason why I feel Hamiltonian neural networks are still performing a little bit better is because of the fact that real life systems, even though they do deviate from ideal systems, they maybe don't deviate in the same rate that we expect it to, if that makes any sense. Because again, uh, if we talk
So I
about,
guess
let's say,
you've looked at more. You looked at a couple of things like this. Are they doing things beyond like sort of what's the most complicated system that you've seen modeled with one of these H&N neural networks?
okay, I believe the most complicated model that they did have was a triple body problem, and
Okay.
it completely deviated, if I remember correctly. Like it did perform better than baseline models, but there is still an underlying problem because of the time evolution that does mess up when like things get a little bit too complicated to model properly. And that is an issue that we do have in Hamiltonian networks, but I believe it's a separate issue from this one. The reason why our ideal, or rather the real pendulum, is still pretty effective, right? But let me rephrase. So the reason why the Hamiltonian neural networks is still kind of working better than the baseline model is because of the assumption that the rate of decay or the total energy in different systems does vary from place to place. So if I take an example of a real pendulum for say, from at least from what I've seen in high school, I the rate of decay of energy is kind of low. So I guess what you were saying about the observation period is completely true, because if we do observe it for longer periods of time, I do believe it's not going to be the same as the system after a certain point of time. So I believe what we are ending up with here is Hamiltonian networks do enforce the energy conservation law pretty strictly, and that also works for in their favor. And in other more complicated example, it does fail. But
Hmm.
the general consensus seems to be that for most systems, the Hamiltonian modeling is a little bit better, if not far better than traditional networks. At least this has been my observation and the author's observation.
Okay.
All right.
This is just some good simplifying. Well, you choose to look at systems that you know you have a strong prior that they actually have energy conservation or approximate energy conservation, like the short time pendulum. And then you said that it failed for the three body problem. This was a idealized three body problem.
Yes, this is an ideal three-body problem.
Okay. All right. Thank you.
All right. Thanks. All right then. This is what is pinned out. Oh, oh wow. Okay, adaptable H&Ns. So, how exactly does it improve on the traditional models? If you have a look. Interesting. Okay. Hey, Ricky, can you hear me? believe there is some issue with your mic.
Hear me? There you go. No, I really haven't looked into it because it kind of seemed way too much for me at that time. But now we could kind of look into it. But it seemed like they
Oh, wait, I think your audio messed up once again.
hello. No, I'm still here. I'm still here.
Oh, okay.
But I didn't exactly get what it did there. But what we're trying to do is something on the root of, I don't know. I think it has way more constraints than, like, let's say a, like, way more specific constraints compared to like generic HNNs, which makes it better for like specific nonlinear systems. Does that make sense?
Yes. Okay. Yes, it does. Yes, it does. I'm going through the paper and I can see that they have a predefined Hamiltonian for these specific systems. So I believe they are modifying them for different systems.
Exactly. Like if people are more interested in like other, rabbit holes, there are more of them, by the way.
Wow,
It's crazy.
this is
It's
pretty
crazy
interesting.
how this gold mine was like hidden so like for so long. Yeah, it's so crazy how this gold mine was like hidden for so long.
I mean, honestly, I'm like completely blown away with this.
I know,
Oh
right?
wow.
Because I was looking into, I think, quantum machine learning. Yeah, I was like doing a lot of quantum machine learning, and this is where I see it like being used mostly. Like it's not being used in like normal systems, but when people are trying to optimize quantum circuits, they use a lot of HNNs because they want to consider the system or a quantum machine or like a quantum system, and this like the judgment ends up being used a lot to like I guess measure between like the quantum system and maybe an actual system, but they end up being used a lot in like quantum machine learning like research or um literature.
And I can see why. Okay, I
Yeah.
am pretty fresh to quantum computing and quantum machine learning, but I can totally see how they can use the modified Hamiltonian networks.
Could you send me a reference to the user HNNs in quantum computing? One sec, yeah. Should have them in my logs. Yeah. There you go. There's a lot of stuff. It's just crazy. It's just crazy. And this has happened like recently.
I Nice.
I know,
See,
right?
I think that is pretty interesting because
It is.
from what I
I
had worked on, or
Go
like
ahead, please.
as I think if we can democratize these models through a proper platform, it would be pretty nice. That's kind of why
Yes.
I started working in on integrating these with DeepCam because they really seemed to be interested in working on this model. So, and
All
plus
right,
it kind
makes
of matched
sense.
with my undergrad degree. So that's how I got into it.
Fair enough.
Oh, this is crazy. Thanks a lot for this paper, though. Like, I'll
I
have to
know.
read through it once again.
Go ahead, go ahead. Just feel gold mines. Go out there.
True. One inherent issue with Hamiltonian networks that I believe they might have solved is the fact that we cannot use specific like generalized coordinates. Even though I am mentioning generalized coordinates a lot, the issue with the implementation of HNNs is that they use canonical coordinates. or rather they fail on if we have something very general. So
Right.
I guess
Yes.
if this is something that they might have improved on, that's worth looking into.
But maybe
Just to
like you.
be
Go ahead.
Yeah, just to be clear, so there is no NNNs. They're not nothing that they're claiming is as a Newtonian neural network. There's just the baseline, which is sort of I arbitrarily try to guess the derivative based on the current positions, and then with sort of no structure in between. And then there's H and N's, which is I have to have a scalar function at some point, which it's the symplectic gradient for. But of course,
Yes.
yeah. But
Mm.
the equivalent thing, I mean, energy conservation in Newtonian mechanics comes from having force laws that only depend on position. So the equivalent thing would be like having a force law that only depends on has no like cross terms essentially between position and momentum. So like you can't have curl, etc.
Right. Right.
I believe
Sorry,
that
that
is
was
the
not a
case.
great explanation. Like if I have a static magnetic field, it's no longer a conservative field. You know what I'm talking about.
Yeah.
Right, that's
I get
one
what you
issue.
mean.
Okay. Anyway,
But there is
um,
something that might be a bit relevant here because there's a recent Springer article that was actually on Newtonian networks only. So,
Newton and PIN. Interesting.
yes. So I haven't actually gone through this entire through Newtonian networks because again, I was under the assumption that it is pretty difficult to create a system that could actually work on it. And also, like the biggest issue that I felt was that if we use the Newton's method to actually find out the equations of motion, more often than not, you have issues with the frame of perspective. For example, if you have like a simple pendulum and if you add another force onto it, it becomes very difficult because you'll actually have to add a virtual force to include
Yes.
that into your frame. So that was an issue that I felt. But if they can
Yeah.
actually solve it, or rather, if they have solved it, it is going to be pretty interesting.
Because I
sorry, I
was
didn't understand
using.
what you're saying. If the observer's coordinates do not start accelerating, you have no fictitious forces. You're saying I'm applying. Sorry, what was the setup?
Okay, I'll just frame it in a better way. What I was saying is ki, if you have static frame of view, so in that scenario, the neural network is going to work perfectly fine because you don't have to add a virtual force. But if your frame of view is accelerating, that's kind of where the Newtonian method kind of starts to break down, if that makes
Sure,
any
sure.
sense.
That makes perfect sense.
Yeah. Because
But
like I did implement one Newtonian PRN for like a fluid dynamics problem, and yeah, as soon as you like start increasing sample points, it starts breaking up just because it doesn't have an idea of like with respect to each data point. Like because I would simulate each point in a um each data point in like, like as in pixels, but I represent them wholly as like one system, and it breaks up. It does like a lot of systems to keep track of because they would need to like track each other. So I think that's what something that could be implemented better using Lagrangian Hamiltonians, I guess, because it's going to be
uh,
easier to generalize.
exactly. Yes, if we are in like as soon as we bring generalized coordinates into the mix, everything just becomes a lot more straightforward. And that especially seems to be the case with Lagrangian networks. And I think this is a good segue to go into LNNs. So, Chad, if it's fine with you, I'll send you the link for that as well.
Sounds good.
Just, all right.
Was like what you said before about LNNs just makes a lot of sense about what like how it could be used for my problem that I was facing. So if I had a lot more generalized way of representing my equations, it would be very easy for each data point to be updated over time with respect to each of them, and it could be like super parallelized. And in that case, it doesn't run into an issue where it's not. I mean, one's not updating before the other, and they update all of them each like to get almost like sequentially, or sorry, at the same time, or maybe one before another, and the whole data chain doesn't break up. Because like what happened in my case was it's breaking up if I had like too many points go like simulating together.
Oh, okay. Okay. Okay, I can see how generalized coordinates can help with that. And that also, I think, gives a better reason to why like Lagrangian networks might work a little bit better in this scenario. So,
Right.
okay, before I believe the best way to understand when you would want a Lagrangian network over a Hamiltonian network is when your coordinates are truly arbitrary, right? There's a difference between a
Yeah.
generalized coordinate and arbitrary coordinate. And I believe that is best explained through Poisson brackets. So if we go to page number 2, yes. So page number 2, equation 1 is the best way to understand the issue that we face with the coordinates that we have in our Hamiltonian neural networks. So while these models were basically refers to Hamiltonian neural networks and a couple of other models that use the same idea. These models were able to learn effective conservation laws, but the Hamiltonian formalism requires that the coordinates of these systems have to be canonical. Now, what does canonical mean? It basically means that your input coordinates have to obey a strict set of rules that are given by your Poisson brackets, right? So it's just a set of three ways that you can, not exactly three ways, but rather this is how you use a Poisson bracket, right? For if you have, let's say, if you have a multi-coordinate system where I and j are referencing to two different coordinate systems. So in that case, your Poisson bracket will help you understand that, let's say if you have qi and qj, if you try to find the Poisson bracket from that, the it's always going to be zero if your coordinates are different. If that means I is not equal to j, and the same goes for your momentum as well. And if your hold up, yes. So in the third case, if you see the Poisson bracket of qi and pj is basically equal to del of ij, which is your signal, which is mathematically speaking just a constant value over a infinitesimally small amount of time. So that's what it signifies. All in all, what
Uh,
this entire
sorry.
jargon is, pardon
So
me.
all this is setting up is like which momentum coordinates are supposed to be related to which position coordinates. So there's no argument here about like infinitesimal amounts of time. Basically, the definition of the Poisson bracket is the thing that you see on the next line, where FG, this, right, these set of partial derivatives. So the point of the Poisson bracket is like if I want equations of motion for an arbitrary observable rather than for coordinates, which generalized coordinates are basically just arbitrary observables. There's one equation that describes that, which is the Liouville equation, which basically says the full derivative of your observable is equal to the Poisson bracket of your observable with the Hamiltonian. So if you think about that for the standard coordinates and what you need to do to reproduce Hamilton's equations that you showed on the previous slide, you basically need it to have to only appear with a Poisson bracket when you match the position coordinate to the momentum coordinate in the same direction. So like what you can imagine is that F here would be H, and then G would be like QI. And you can see that in order to, if you had like pi squared as your kinetic term, the only thing that would produce the correct pi is m times your velocity, would be if you had a Kronecker delta. Kronecker delta just means that it's 1 when I and j are the same, and it's 0 otherwise.
All right. Okay. Okay. So the chronicle delta function, all right, which is the sigma symbol, if I'm not wrong,
The
right?
delta on in equation 1, the delta ij,
All
that's
right.
the
So
Kronecker
delta I
delta.
just okay.
Over on the
All
right.
right. Okay. Okay, that makes sense. So, okay, the through the literature of whatever I understood through whatever the authors were trying to establish is the fact that for these canonical coordinates to work, if I guess a better example to understand would be in slide, I believe page 5 of the paper. Yes, with the diagram, I believe. So this is kind of how I visualize the understanding of how why HNNs kind of fail at arbitrary coordinates and how LNNs can actually work in certain scenarios where your coordinates do have to be arbitrary. So I believe even though the mechanics or rather the solutions provided by both the models are theoretically pretty similar in performance. The only advantage that LNNs do have over HNNs is this, the fact that they are able to work perfectly fine with arbitrary coordinates. So I believe that's the biggest triumph. And as far as the model performance goes, again, as we saw in Hamiltonian neural networks, it is performing a little bit better than baseline models. And the interesting thing that we do have here is that it's showing the results on a different set of problems that also kind of puts into perspective how well the models are working, especially in if we see wave equations as well. So that's something that Hamiltonian networks didn't work on. All in all, the main difference between both the papers seems to be the lack of arbitrary coordinates in HNNs due to the constraints of the modeling itself, and the addition of arbitrary constraints in the Lagrangian model, and the fact that they actually worked on a new set of problems. So, all in all, it does seem to be that both of these models are kind of they offer separate solutions for separate problems. It's not like that one of these models is actually better than the other one in any regard. So that's one thing that I found out.
Sorry, one question here. So for LNNs, you said that it's good with like arbitrary coordinates. So isn't it like strictly better than HNN since you have to like manually, like base like HNNs better than LNNs?
I don't think I got the question properly.
Sorry. You said that HNNs and LNNs are kind of good in different like tasks, but from your arbitrary coordinate discussion, I imagine that LNNs are like strictly better, but ways like HNN is better than LNNs.
Uh, I believe that is the case for the problems that we saw in HNNs, because if we go from a side-by-side basis and like see which models are actually performing better, we would see that none of the actual models are the same. So the problem solved in NNNs and the problem solved with the Hamiltonian networks is pretty different. So that is why I'm not too confident about giving a judgment on that. And I think because there does seem to be like a lack of experimentation, so that also puts it into perspective that there is, I would say it's kind of like a confusing scenario here, because it seems that the authors purposefully didn't want to go through the same problem sets. Either that could be to show how inclusive both of these models are, or to show that there is no proper way to identify which model does work the best in the given problem. So that does seem to be a gray area.
So basically,
Um,
sorry, go ahead.
I was just going to ask, could you post the DOI for the one we're looking at right now? Sorry, I'm confused. There are too many links now. I can't find which paper
Sure,
this
sure,
is.
sure. If it works, I'll just send all of that in a single link. I believe that might be a bit useful.
Okay.
So basically, what you're saying is that for LNNs and HNNs, they can technically solve like physical tasks, but since the authors didn't compare them in a benchmark, we don't know which is better, basically.
Precisely. And I'm not exactly sure if the authors did it on purpose because Sam Gradanas has worked on both of these models. So it does put into question what exactly were they trying to achieve by having these different problem sets.
Okay, thank you. So basically, like LNNs, we can just choose pretty much random coordinates that follow a certain constraint, and for HNNs, we have to like have like strict canonical coordinates. Is that like a good okay understanding? So,
I do believe that this is exactly what's happening. So if you model the training data in canonical coordinates only, we would find that your Hamiltonian networks will work perfectly fine. Perfectly is a stretch, but yes, they will work without the issues that we see when we don't use canonical coordinates.
got it. Thank you.
All right, and I've also sent the three papers, the Lagrangian Hamiltonian, as well as the adaptable HNNs that Ryuki just sent a couple minutes ago. So I guess
Wait, so
that's it for the most.
just so I understand correctly, is when with the HNNs, they always just assume that the derivatives are the gradient of some scalar function. Is that right? Like there, it's not like when they do HNNs for these problems with weird coordinates, they have some other like thing that attempts to do some coordinate conversion or anything like that.
No, in the original Hamiltonian paper, they explicitly mentioned that the Hamiltonian function is going to be scalar.
Right, the Hamiltonian. I guess that makes sense. That the Hamiltonian function will be a scalar. But what I mean is that like if you are hoping to solve a problem with general coordinates in the Hamiltonian picture, you need to do a conversion, basically two canonical coordinates, then get the derivatives there and convert back. That's basically what Liouville's equation is. Uh,
Right, okay.
when they show these comparisons between an LNN and an HNN, is the HNN just have no? It just pretends that the general coordinates are canonical. Is that? I mean, that would make sense for like why it performed so badly. But was that the setup?
Yes,
Do you? Okay.
yes, that does seem to be the setup. And honestly, it did kind of weird me out the first time I read it because honestly, that doesn't give much ground for improvement, or rather, there is no apparent improvement that Lagrangian networks bring, except for the fact of the arbitrary coordinates. But other than that, there is no real way of comparing both of these models. And whatever comparisons have been made do seem a little questionable, if I can say that.
Yeah. I guess it seems like the thing that's been confusing me for this whole talk is like you know Lagrangian, Hamiltonian, Newtonian pictures are all fundamentally identical, and there's like some like theoretical convenience in that like it's easier to write certain things down, but like numerically, if you're doing reasonable things, it you should basically get the same answer whichever picture you're doing it in. And so, yeah, it's confusing to me, and it seems like they're sort of the tests that they're choosing are kind of arbitrary and leading to a result that has more to do with how they set it up than really like one picture versus another. But whatever.
Yes, and I'll be honest, it's just a little bit weird to me. I can understand why they would want to use Lagrangian and Hamiltonian networks because it does make perfect sense. If you want to compute something, you would want a general template. But the fact that they did not have any baseline for comparing or an evaluation benchmark or anything else that can kind of give a substantial that can give substantial evidence that yes, these models do give equivalent outputs, and if they don't, they have an underlying reason behind it. Basically, all they did with both of these papers was introduce new methods, and which in themselves are very innovative, but they didn't give a proper metric for comparing both of these models, which in my opinion is probably the biggest drawback because it leaves the author in like the reader in a weird state where they don't understand key. If there is a specific problem set, which model should I use and why is that model objectively better or worse? That just kind of it's just I mean I'm just a little bit confused. I'm just as confused as you were when I was first reading it.
Yeah.
I still
Right
understand.
as of right now, I'm where with what Chad said earlier, which is just like seems like I need to have a strong prior that I'm doing this in the correct coordinate system for the H and N, and with the LNN, I don't need that, and there was no other comparison. So sort of with no other information, it just seems like the LNN is always the better thing. But you mentioned that you thought that was not true. Is it?
No, no, no. Rather, I was agreeing with you. I just feel that there is no objective way to compare them, and that
Yeah.
is pretty shady, if you ask me.
Okay. Thank you for the
I
talk.
thank you for being here. I mean, I can understand there might be a little bit of an issue because of a language barrier, but it was really fun. It was super fun going through these models and understanding how they work. So that was fun. And thank you everyone for being here. I mean, I don't know what else to say. I'm really, really glad that all of you joined in, and especially you, Chad. Thanks a lot, bro. So, thanks a lot, everyone. I hope you liked it. I'll make sure that the next time, if I do actually do another reading session, I'll have a lot more material to work on.
Thanks for presenting. It was an awesome presentation.
It was great.
Thanks a lot.
That's great presentation, by the way.
Thank you so much. Thank you so much, everyone. Uh, I am I'm really glad that you all enjoyed it. But yes, next time if I do have an idea to present, I'll be a bit more articulate with that because I did feel that many points that I wanted to express might have been pretty confusing. Had I given a bit more time to them, I think it would have been easier to understand. So I'll work on that.
It's a confusing area on its own because I'm still confused at this point. Why should I be using LLMs instead of classical Newtonians? But I don't see a reason like until now, like practical reason or for like this kind of data should be using LLMs because they generalize and they give me better results or at least get me faster. And just because it's faster, it's more accurate rather using Newtonians because they're lacking behind over time and I lose it. I mean, I'm getting a lot more loss compared to uh HNNs like LLMs. So yeah, I mean, I get the point. I think there has to be a bit more research into this before we could actually start using them to like very practical stuff, I guess.
Right, and that's kind of why I'm working with DeepM on this. It was ideally supposed to be my GSOC project where I implement both of these models, but the deeper I went into it, I realized that if there was a simpler way to assess both of these models, that might be pretty good for the community. So let's hope I get it done over the summer. Might be a useful tool. I don't know.
Good luck to you then.
Thank you so much. Thanks so much.
Sorry, I have
All right.
I just thought of two questions. One was one was like one thing I thought these papers were meant to do was like give like inductive bias so that the model is like more biased to output the right answer. So is that like a good like assumption?
Uh, could you repeat your question once? I guess I got a little lost.
Sorry. It's like the idea of these networks may need to like keep an inductive bias so that the model is kind of more biased in like a certain way to output the correct answer, kind of.
For HNNs, that does seem to be the case, although I believe it's more of a result, or like an aftermath of using the conservation law, and not really taking into the fact that there are different conditions for different systems, especially real systems. So I guess that is true, but I believe that's where the adaptable networks have improved. Again, that's something that I'll have to read into, but yes, I do think that is the case here.
Okay, a follow-up question is for like HNNs, like the conservation of energy is like always true, but do you think that it's still true for LNNs?
Um, Wait, I think that might take a little bit more explanation, but for HNNs, it is a specific constraint, but that's not the case for LNNs.
Okay,
Because for Hamiltonian networks, your entire goal is to conserve the H value, and the LNNs don't actually have that constraint because, again, the goal is not to make sure that H is conserved, but rather the fact that it complies with the Hamiltonian rule, if that makes sense.
interesting. Gotcha. Yeah, I think that's all for my questions. But anyone else has questions? Okay, yeah. Thanks again for the awesome presentation. And for next week, I'm not sure, but maybe we will do like a tutorial on Triton. But yeah, overall, thanks for everyone for attending. Yeah, do you have any final thoughts or anything?
None from me. The one thing that I do think is worth noting once again is that both of these models are presented as alternatives rather than an improvement over one another. So I believe if we can set the narrative clear by having proper research done on both of these models, I believe not that this is not only going to improve the quality of the research that they present, but it's also going to give a gateway to more sophisticated physics informed networks. So that's something exciting.
Got it. Thank you so much for presenting. And yeah, hope you all have a great day and I guess a great weekend too. And see ya.
Likewise, likewise. Have a great weekend, everyone. Thank you.